So the goal is to be able to use the converse of the Pythagorean theorem to determine if a triangle is right, acute, or obtuse. And we know conditional statements can be written in the form if P, then Q, where P and Q are statements, often expressed with this little arrow here. And an example of that might be if it's raining outside, then it's cloudy. And we can say conditional statements are, true or false. But the converse of that would simply be the reverse, Q then P. Not everything that's true one way is true the other. So if it's cloudy outside, it's not necessarily raining. And I'm sure you could think of a situation where it's raining and not cloudy, but I think you get the idea. So with the Pythagorean theorem, let's talk about what that conditional statement is, figure out the converse, and then discuss ways we can use that to determine whether a triangle is right, acute, or obtuse. So the Pythagorean theorem as a conditional statement could read, if it's a right triangle, then a squared plus b squared equals c squared. And really, to be more accurate, or precise rather, we should say the sum of the two squares of the legs is equal to the square of the hypotenuse. Or that is, a and b have to be the legs for this to be true. But I think we know what the a squared, the a, the b, the c generally represent. But so the converse would just simply say this backwards. So if a squared plus b squared equals c squared, then it's a right triangle. And so without even looking at, I guess you could say, without even looking at the triangle itself, if we just had the side lengths, we could really determine if it's right. Well, then by default, maybe we should be able to determine if something's acute or obtuse. So let's think about that for a moment. What would happen if a squared plus b squared does not equal c squared? Then, ... that becomes the question. Well, you might wonder, or ask yourself, what are the two ways something can't equal another? Well, we could say then that if a squared plus b squared does not equal c squared, we could rephrase that into two particular statements. So if a squared plus b squared is greater than c squared, then ... And if a squared plus b squared is less than c squared, then... And so I guess the whole of this video is really just going to focus, the rest of it's just going to focus kind of on, I guess you could say, these three statements, or really these particular two right here. What happens if the sum is greater than the hypotenuse squared, the sum of the sides squared, or the sum of the legs squared is less than the hypotenuse squared? So you may have heard of Pythagorean triplets. That's three whole numbers that satisfy the Pythagorean theorem. A squared plus b squared equals c squared. So in this case, we could think of 3, 4, and 5. Now, if you were just given those three numbers and told they were assigned to some units like centimeters or inches, and they were side lengths of a triangle, determine if it's right, we could plug those into the theorem and see if it was a true statement. So, in other words, does 3 squared plus 4 squared actually equal 5 squared? One thing I want us to be careful of is assigning the correct variable to the correct number for the equation right here. So we know C has to be the longest side, that's the hypotenuse, and then it doesn't really matter which one's A and B because addition's commutative. So in this particular case we know it works because 9 plus 16 does equal 25. So that just means if you're given these three numbers and asked whether or not it's a right triangle, you can determine whether or not it's a right triangle by simply plugging them in and seeing if it works. Anytime three whole numbers work, we can call those Pythagorean triplets. So let's do an example now where they don't work, and then how might we determine whether or not it would be acute or obtuse? So if we were given the three numbers 3, 4, and 6, again I want to attribute C to the longest side, and then A and B don't necessarily matter. But real quick, I just want to quickly review, there's really three different kinds of triangles in the sense of acute, obtuse, or right. And a right triangle has one right angle and two acute, two angles less than 90. An acute triangle has three acute angles in it that all add up to 180. And I think that's important to remember, all the angles in a triangle add up to 180. So then an obtuse, let's see if I can draw something that's obtuse. Oops. An obtuse triangle has one angle that's much greater than 90, or at least greater than 90. It could be 91, it could be 90.5, then it would be obtuse. But the sum of the other two angles has to be something, therefore, less than 90. So they're both acute, because the sum of the entire, of all the angles has to be 180. So obtuse has An obtuse triangle has one obtuse angle. An acute triangle has all three acute angles. And a right triangle could be thought of in much the same way as an obtuse triangle because it has one angle of 90 and then two acutes. Similar to the obtuse because it has one obtuse and two acutes. So using these numbers to determine that, if we plug these in and we say, okay, well 3 squared plus 4 squared, how does that relate to 6 squared? Is it equal to? Because if it is, then I know it's a right triangle. But if it's less than or greater than, does that mean it's acute or obtuse? Well, let's use these numbers as an example. So if I have 9 plus 16, that's going to be less than 36. So less than 36, because that's 25. 9 plus 16 is. So what does it mean if the a squared portion plus b squared portion, if that whole side there is less than c squared? Will that indicate a obtuse triangle or an acute triangle? Let's determine that right now. So if we were to imagine what an obtuse triangle does is it might compare to its right triangle. So let me try and draw something that has similar length size. So we'll call this A, B, and C. And then I'm going to be try to careful to keep A about the same size if I can, and B about the same size if I can. Oops. But I didn't want to do that. I want to do it obtuse. It's kind of hard to keep B the same size. It might be a little bit too long there. But the question becomes, what really happened to C in this case? So you might notice that A is about the same size, B is about the same size, but C got longer because the angle opposite of C was larger, so the side C had to therefore become larger to stretch. As the angle opens up, as this angle opens up here, this side has to get longer. So this is an obtuse triangle here because it's got one obtuse angle in it, so it's obtuse. So if C is getting longer, it makes sense then that this would be reserved, this statement right here would be reserved for obtuse triangles. Because the side C got longer, so its squared value is now going to become greater than a squared plus b squared. Because we know in a right triangle, that they're equal. So it makes sense if we've enlarged C, then all of a sudden C squared would be larger than the sum of a squared plus b squared. So in that last example we had, I believe the last values we had the values of 3, 4, and 6, and when we plug those in, we had the statement that 25 is less than 36. That is, C squared was greater than the sum of a squared and b squared. So that means that that must be an obtuse triangle. And that can be difficult, I think, to maybe wrap your brain around. If it is, I really would encourage you to break out a ruler and draw an protractor, draw an obtuse triangle, measure the sides, and see if this is true. Square them, so measure side A, side B, side C. Square them and see if C squared is greater than. So, anyways, that was for the right. I hope that's helpful. Let's talk really quick about acute and why the acute would make sense. But you probably already figured that out. If this is obtuse right here on the top, then acute must be when a squared plus b squared is greater than c squared. So yeah, what about a situation like this where a squared plus b squared is greater than c squared? Well, if we want to think again about a right triangle where they're equal, so we'll make this a, this b, and this c. This is a right triangle. In this particular case, a squared plus b squared equals c squared. But in an acute, all three angles are acute. So we've got a, b, and c. I've tried to keep a and b roughly the same size. I can't do it exactly with this set of software that I'm using, but we can see c got shorter as the angles change. Relative, and when I say that, I mean relative to a and b. C is smaller relatively to a and b than it is over here in the right triangle. And so if c got smaller in an acute triangle, it makes sense then that the sum of a squared and b squared would become greater than c squared. So this statement right here must be reserved for acute triangles. And so if we had three numbers, if we were given three numbers, like, let's think, maybe we're given 2, 3, and 3. It's possible for acute angles to be isosceles. It's also possible for right and obtuse angles to be, triangles rather, to be isosceles. But this would be an isosceles acute triangle, I believe. Once we plug in the numbers, we'll find out for sure. So I'm going to attribute C to one of the longest sides. Because they're tied for the longest, it doesn't really matter which one I choose. And then these two can become A and B. So we'll square those. So how does 2 squared plus 3 squared, so that 3 squared, how does that actually relate to C squared, question mark? I'm not sure how they relate yet. So 4 plus 9, how does that relate to 9? Well, it's obviously going to become larger than 9, and that's because, 9 plus 4 is 13. And so that must be an acute triangle. Anyways, I hope this video was helpful for you. In the next one, I'm going to do one right after this where I do a few examples where I'm given a set of 3 numbers and then I determine whether it's right, acute, or obtuse. All right, thanks.